All right, so welcome back. Our second speaker of the morning is Dariusz Kosz from the Basque Center for Applied Mathematics, and his title includes maximal operators on the infinite dimensional terms.
Okay, so thank you very much for this kind invitation, and I'd like to say that this is a pleasure for me to have a talk here. And my presentation is based on the following article, maximal operators on the infinite dimensional torus, which is a joint work with this finite set of mathematicians. So we have two people from Spain, Javier Martinez Perales and Luz Roncal, and two people from Argentina, Victoria Paternoster and Ezequiel Herrera. And the funny thing about working in this group of people was that during the preparation of the paper, I was in Poland, and at some point, and there was a time where Ezequiel Herrera worked in China. So at that point, we formed a fairly good covering of all time zones on the planet. So it was especially hard for us to arrange a Zoom meeting, but okay, we succeeded with this. Okay, and so this will be our setting we work with. So infinite torus, as before, Haar measure, which is a product of Lebesgue measures on one-dimensional torus. The metric. I don't want to use this formula anymore, but okay, just to determine the topology. And here we have basis, which is just a collection of open sets, so with a positive measure, and associated with this basis a maximal operator, which is defined in the following way by using the averages. So here is the notation we use. The averages over elements of our basis. Exactly those who contain our point X. Okay. Okay, and the topic of this presentation will be exactly so how to determine the interplay between the structure of a given basis P and the properties of the associated maximal operator. So what about the properties of the maximal operator? So we have well-known types of estimates. So strong type estimate, weak type estimate, and restricted weak type estimate, and they all can be in some sense explained in terms of Lorentz space. So here we have boundedness between from LP to LP. Here from LP to LP infinity, and here is what exactly inequality must be satisfied. And a restricted weak type, which is boundedness from LP1 to LP infinity. What should be mentioned here is that this quantity for all lambdas is at most the LP norm of a given function. So being of weak type is easier than being of strong type. And for restricted weak type, we have that for P equal to 1, this is just a weak type estimate because L11 is just L1, so nothing else than just weak type. And for P greater than 1, we have nice characterization for our maximal operator that the being of restricted weak type is the same as satisfying this inequality for indicator functions. So this is all standard. Okay, and our important bases are the following. So Rubio de Francia basis R, not dyadic one, but with all translations, and R0, so the dyadic one. Okay. Okay, and just a quick reminder. So we use this collection of fundamental domains. So our goal is exactly to divide each of the infinity many variables infinity many times. So we can use the order like this, for example. This one is very convenient because at some point we have an element which is of the form 0, 1 over 2 to the power n times, and then the torus. Okay. Okay, here we have this collection of subgroups and this quotient group. And then if we allow all translations, then we get this basis R. And if we allow only translations connected with elements from subgroups, then we obtain this dyadic basis R0. Okay, and about the properties of maximal operators associated with these two bases. So if we look at R0, then it happens that it is of weak type 1,1, and this is all very standard. But I would like to just show you the proof because it is just very easy and fast and short. Okay, so we use this property that for two elements of our dyadic basis, we have exactly three options. So either one cube is contained in another, or the intersection of them is just an empty set. And because of that, it will happen that maximal operator is of weak type 1,1. So just somehow just marking a property in some sense. Okay, and in the weak type 1,1 estimate, we want to understand what is the measure of this set. And if X belongs to this set, then there is a say cube at which contains X and at which the average is greater than lambda. And then because of this nestedness property, we have that if we look at maximal elements where this average is greater than lambda, then these maximal elements are disjoint. And of course, the average there is greater than lambda. So we have this decomposition of the level set. Okay, and it is important that here we have disjoint sum. Okay, and then if we want to estimate this quantity for say lambda from here and say non-negative function, because we can test the maximal operators on non-negative functions only, and we will do that during this talk. So if we look at this, then we can split the measure as follows. And then we use the fact that on each particular cube, the average is greater than lambda. So we have the following inequality. And then we use the fact that the sets Q, K are disjoint. So this expression is at most the L1 norm of our function, initial function F. So we obtain a weak type 1,1 inequality with constant 1. And so this is all very standard. And after using a Martin-Kevich interpolation theorem, we get that this maximal operator is of strong type PP for all P greater than 1. Okay, so this is about this is the story about maximal operator with R0. And what about R? So here also the results are pretty easy to obtain, and we get that this maximal operator is not of weak type PP for all P which are finite. So without P infinity, because for P infinity it's clearly bounded with constant 1. Okay, but what is the reason? So the idea is that with all translations we can in some sense embed a piece of Rn with arbitrarily large n into our infinite torus. So we do it by using the following cube, which is an element of R0. So we use n first coordinates here, and then we use, for example, this translation. So here we have our center cube Qn. And then we translate it in such a way that we use first n coordinates, and in a way that here the translation is in proportion 1 to 2 to the side of this cube. And then we just test our inequality on a function which is just an indicator function of this center cube. So the LP norm is like this, so the measure of the cube to the power 1 over P. And then we realize that on these, say, wings, here there are n wings, which are disjoint. The maximal operator is at least 1 over 2, so strictly greater than 1 over 3. And then we write down this ratio between, for lambda equal to 1 over 3. And then we we get that the measure of wings is comparable with n times the measure of the center cube. And with n going to infinity, we easily get the result that this operator is not like pp for any p which is finite. Okay, that's the story about R. And now another question arises. So what about, say, intermediate bases? So we want to fix a collection of say cubes contained in R, maybe containing this R0, and then we want to ask if some more peculiar results can be achieved. Okay, and here is the main theorem of this presentation. So if we look at the restricted weak type estimates, then any reasonable scenario is possible. And by reasonable scenario, I mean that we can have the following situations. So either we have that there is a restricted weak type estimate for all p's, all finite p's, and this one is realized by R0. We can have a situation that there is no restricted weak type estimates for all finite p's. Okay, I'm sorry. Here I restricted our range of p's to 1 infinity without infinity, because for p equal to infinity everything is clear. So I excluded here p equal to infinity. This is why here is the answer. Okay. So this scenario is realized by R, and here we have some other scenarios that can happen, but a priori we don't know if there is a basis which covers these cases. So in our talk we will show that they also can be achieved. So we have restricted weak type estimates from some p0 to infinity with p0 included or excluded. Okay. Okay, and some remarks about the theorem would be before the sketch of the proof. So if we look at our intermediate basis, then it is it consists of R0 and some other elements. And because R0 has very good mapping properties, we can focus only on S. And in case if there is some X which is not which not belongs to any element, if there is X which not belongs to any of the elements of S, then we use the convention that then the maximal operator related with S at this point is equal to 0. So this will be just the convention. Okay. Okay, and now because then the maximal operator related with this sum will be just the maximal operator of this, and this guy is bounded on all p's. So we can use this convention. This will be fine. Okay, and another remark is that we to get some interesting results, we should use infinitely many scales. Say so these measures of sets, because these measures can be okay, 1 over 2, 1 over 4, 1 over 8, and so on, because these are the translations of dyadic cubes in our setting. So if we use only finitely many scales, then nothing interesting happens. And this is just because then we have this pointwise estimate that if we take any point x and we want to estimate the maximal operator at x, then we can get at most the mass of the function, so the integral of the function on the whole space, taken with respect to the whole space, divided by the smallest measure of our set that we can put here, and then we have this nice pointwise estimate, which gives that there is also a strong type estimate for p equal to 1. So then nothing interesting happens. Okay, so we need to use infinitely many scales. Okay, another remark is this one is very nice. So if we assume that there is this finite overlap, which is uniform with respect to X. So we take X and we look how many elements from our basis contain X. If this is bounded by a universal constant, then this constant appears in the strong type 1-1 estimate. And the proof is, again, this 1 or 2 lines, so I will show you quickly. So we want to estimate the L1 norm of the maximal function. Then we use a simple pointwise estimate that we don't look at the biggest average, but we sum all averages. Here we assume that F is non-negative. We can do that. Okay, so we sum all averages, and then we want to explain what exactly this guy is. And so we get the following expression. We want to change the order of integration and summation, so we want to have integration over the whole torus, and here the summation over all elements of our basis. So we need to put some indicator functions here, just to make sure that this will be there will be it will be possible to change the order of integration here. Okay, and after all of this, so we use the value of F at some point y, and now we want to count how many times and with what weights we use this F of y. So we put it in front of everything, and then we count this guy. And here, if we look carefully, then it happens that this integral times 1 over the measure of q is exactly 1. So we have as many ones as large as our overlap at our point y. And if this guy is uniformly bounded, then we get that pointwise this weight will be estimated by n. So we get the following bound. So I think this one is very elegant and good to know, but also I mean standard and easy. Okay. And another remark, I don't want to get into the details here, but you can look only on countable sets, because if we have some basis which consists of uncountably many elements, we can somehow approximate by a countable family in a way that these two maximal functions will coincide for all the functions from LP for all we want to consider here. So okay, these are the remarks about our main theorem. And now, what about the proof? Okay. So before the sketch of the proof, we need just one more definition. This will be the key definition, which will lead us to the proof. So we have a configuration which we call epsilon L configuration around a cube Q. So this will be a member of our dyadic basis, and then we use similar structure as before, but with 2 parameters. So this parameter epsilon is a small parameter which defines the proportions between the side length and this translation. And the second parameter is just how many coordinates we should use. So how many translations we consider here. So to do it properly, we need our central cube to have at least L non-free axis. But we can do that just taking this, for example, this cube 1 over 2 to the power of L times and times the torus. And then our basis will consist of these red elements. So only these translations will be counted. But somehow this central cube will be useful for us to test the maximal inequality for indicator of this central cube. Okay, so, and we call this set of these guys that they are wheels. Okay, so as I told you, we test maximal inequality for F equal to the indicator function of this central cube. So the LP norm is like this. And then we realize that the maximal operator, if we look at wings, is equal to epsilon. And this is just because of the proportions between this overlap here and the measure of this set or this set, they are the same. Okay, so I would like to emphasize here that this is all about proportions, not about the measures, the measures of particular cubes. Okay, and then if we look at this ratio, then it can be estimated from below just using lambda equal to epsilon or epsilon divided by 2 anyway. We get something like this. So here we have LP norm of f, and here we have lambda times the measure of wings. This is an estimation from below, so we can use this. And then as our parameter epsilon is very small, we can just get rid of this term, and then the measure of Q will cancel with this one. And then we get a nice expression which uses both parameters of our configuration. So at the end of the story, we get the following nice expression. But this is for testing maximal inequalities on very specific functions. Okay. And now sketch of the proof. So we would like to obtain some basis for which there is this restricted weak type estimate, but only for p's greater than p0, with p0 either included or excluded. So we need to carefully look at this expression and use it. Okay, so at step 1, we need a sequence of these epsilon L configurations, just to make sure that okay, we have a sequence of expressions of this type, and for some piece it will blow up to infinity, and for some other this will be uniformly bounded. This is the idea, and for technical reasons we want these epsilon L configurations to be disjoint. So even if with this central sets included. So for different parameters j and j prime, we have that this intersection is the same. Okay, and then with this disjointness, we can divide our problem into countably many easy problems regarding only one j. And then we have nice characterization that the maximal operator related with this guy. So first we should look maybe at this. Is of restricted weak type PP, if and only if this expression is uniformly bounded. So as we all saw before, so this is maybe something very predictable. This expression is here. Okay, and for p equal to 1, this condition is a bit different, and I will explain why in a moment. Okay, but okay, this is step 2 of our proof. And then it is very easy to finish our argument, just because with this characterization, it is just easy to find the right parameters to have. So, for example, here we have that this expression is uniformly bounded only if p is greater or equal to p0. And if we want to exclude this p0, then we just put a logarithm term here, and we are done. Okay. So now we have that step 1 is somehow easy. It makes you that step 2 can be written for with this supremum here, and just by looking at single configuration. And now step 3 is also an easy consequence of step 2. So this is the core of the proof, and I would like to explain it in a moment in more details. Okay, and okay, this time I would like to first mention this p equal to 1. So we have the following characterization, and if we look at our epsilon L configuration. So these red sets are the sets that are considered as elements of basis. So if we work under this disjointness assumption, then we get that that the overlap of this red set is controlled by the second parameter. Okay, and then if we assume that that this parameter is uniformly bounded in J, then we obtain that it must be the case that the maximal operator is of restricted with type 1,1 because it is of strong type 1,1 by this uniform overlap I showed you before. Okay. So this this case is easy, and the reverse case is also easy, but interesting. So this time we should test our maximal inequality, but not taking the indicator function of the whole cube, but of this bottom right corner. So these points from bottom right corners are better in the sense that the overlap of these red cubes is the highest there. And for p equal to 1, it is better to consider this than the whole cube. Okay, so we make some computations. So the L1 norm is like this. So this is a measure of our blue cube times the proportion between them. Okay, and for the maximal operator, we have that here. If we look at wings, then this maximal operator is greater than this, because this is exactly the proportion. So we use lambda equal to this expression, and then we use the measure of wings, which is comparable with the number of variables times the measure of the blue. And then if we look at the ratio, then if this is not uniformly bounded, then the ratio goes to infinity. We should put this in the numerator and this in the denominator. So we get that this expression goes to infinity. Is not uniformly bounded if this is not uniformly bounded. Okay, so this is the proof for p equal to 1. And just another thing to mention is why this condition is a bit different than this. And an explanation is that because to get this, we should use the whole cube as our model example of function that should be tested. And for p equal to 1, it is better to use this. And if we would like to use this corner for p greater than 1, then what we get? So here is the LP norm of our initial function. So this is sorry. Here is the LP norm of our initial function. So this is like the measure of our corner cube, the power 1 over p, and then the maximal operator is just like before. So you take this lambda. Okay, as a test, you take this lambda equal to this expression, and then you use this measure of wings, the power 1 over p, and then it happens that the power for this epsilon j is not 0. So this is like some positive power, and then it happens that this term makes everything less interesting. So let's say. So even if this is large, this can make that testing our inequality on these particular functions is in some sense worse than testing on the indicator function of the whole cube. And for p equal to 1, this is 1. So this is where this say discrepancy occurs. So if we would like to go with p to 1 here, then we may expect that here we will get something like epsilon j times lj, but this condition is different. Okay. And now what about the most interesting case? So p between 1 and infinity, and here, of course, one of the implications is easy by looking at our test functions. So if this is not uniformly bounded, then looking at our test functions, we get that this maximal operator is not restricted. Okay, and the reverse implication is the harder one. And here we use a bit of analysis and probability. Okay, so our task now is to look at a single epsilon j configuration, to take a subset of this set, say, and then to measure this ratio between maximal function p infinity and the LP function of the tested function, because here the LP1 norm is just the LP norm of the initial functions. Okay, and we can split our problem into 4 problems, localizing both the initial function f and the maximal function. So we can do this in the following way. So we localize either to this central cube or to wings, and we have 4 possibilities. And for us, the only interesting one will be the ones as before, that our function is localized to the center cube, and the maximal operator is localized to the wings. And by using some very standard methods like overlap or like disjointness, we can prove that the other cases are not interesting. They are bounded, say, I think strong type 1. Okay, so but the interesting one is the following. Okay, so let's go to the detail. Okay. Okay, so we have the following task. We have this assumption, and now we want to get that for each j, for each u, which is a subset of our center cube, this expression. So this is the maximal function localized to wings with p infinity norm, divided by the measure of our initial set to the power 1 over p, is uniformly bounded in u and in j. Okay. And how to prove that? So we can first we can assume that our level set will consist of m wings for some m from this range. So we can assume that we are in this particular situation. Okay, and now by symmetry we can assume that first m cubes are involved. Okay, so this gives that because of the disjointness of these wings, this means that if some wing is in the level set, then exactly this translation which is related to this particular wing have an average value greater than lambda. It must happen because of the disjointness of these wings. Okay, so now we have some estimate on lambda in good direction. Okay, and okay, and I would like to say that now we can divide our center cube into finitely many regions, which are connected with what is the overlap of these translations on each at each point. So if we look at translations of Qj in first m coordinates, then we want to count how many translations contain a particular point x, and it may be some number from 0 to m, and the measure of each of these regions is exactly this. So this is like in the binomial Newton formula. And I would like to emphasize one more time that this is everything about the proportions, because here this will cancel with the measure of our initial center cube, and then we will work only with expressions of this type. at the end of the story. Okay, and now we make some computations. So we take lambda, and we know that this lambda is smaller than this ratio if we take this and put it here in the denominator. So we can use this for each say each k from 1 to m, and take the average. So we have like this. Okay. So now the measure of each translated cube is just the measure of the center cube. So we put it here in front. And then we, instead of this, we write the integral formula with this indicator function. And then we somehow want to count how many times each x was counted here. And for x belonging exactly to this set, so this is the intersection of our U with this region where this overlap was equal to I. So then this x is counted exactly I times. So we rewrite this expression as the following sum. So we sum from 0 to m, and we just have these measures of these regions where our points are counted I times. Okay, and then okay, what we would like to get at the end. So we can assume that our initial set has measured like a t proportion of our initial center cube Qj. So this t should be between 0 and 1. And with this assumption, so we assume two things: that the level set consists of m elements, m wings, and then that the measure of the set is exactly t times the measure of the center cube. So we have two parameters. Also this j, so exactly 3 parameters, and we want to see that some expression connected with these 3 parameters is uniformly bounded. But okay, how to finish? So now we would like to use this inequality. So we get that lambda can be estimated from above by this guy times this, and now we would like to say that the measures doesn't matter, and this is all about proportions. So in some sense, this guy does not depend exactly on the measure, because here we use that this measure will use this measure of the center cube, so the powers will sum up to 0 in some sense, and then we get that this expression can be at most some expression which depends only on these parameters m and epsilon j, not on the measures of these particular cubes. And this is connected somehow with the Bernoulli distribution, just because of these proportions as here. So if we look at distribution of this type, then the worst case is just if we take a subset of measure t, for which this expression is the biggest possible. So we should proceeding like this, we should take just the interval 0t, and this is some exact expression that can be exact formula that can be expressed in terms of this binomial distribution, this Bernoulli distribution. Okay, so now our really final task is to estimate the following quantity, and then we estimate lambda by these. Okay. Now the measure of the wings here is a type. There should be a power 1 over p here, but okay, this expression is correct. So here we have the measure of wings to the power 1 over p, and divided by the measure of our initial set u to the power 1 over p. And then it happens that as I told you, it is all about proportions. So the measure of cube doesn't matter. So here we have the last expression, and we need to estimate it uniformly in 3 parameters. So in epsilon j, in m, which is between 1 and lj, and in j under the assumption that this condition is satisfied. And then we use some probability methods just to count how many points in how many points this Bernoulli distribution produces something which is much greater than the average, or something like this. Some estimates for moments of this distribution. So some I would like to say maybe 3 pages of tedious computations, but this is the idea. So I would like to stop the proof at this point, maybe. Okay. And now, what is an interesting problem related to our topic is that for the endpoint, we can actually have 4 different types of behaviors. So the first one is that we assume that this is the endpoint of our range where this, say, strong or weak type inequality holds. Okay, so we can have that at the endpoint there is no inequalities of neither of these 3 types, and this can be achieved by looking at our examples. For example, if we take okay, we just need to it's far, but we can just pick P0 and get a basis for which the associated maximal operator is bounded only of restricted weak type is only for P strictly greater than P0 and not for P0. So this is exactly this situation. But there are another situations that may be achieved theoretically, so that we have only restricted weak type estimate at the endpoint for these 2 types or these 3 types. So this remains open if these scenarios can actually happen for some basis. Okay, I think this is interesting to ask about this.
Actually, the column on your right with trivial examples you have it. Right?
Which one?
With a trivial. Oh, but if they are trivial, it's not a basis. Sorry.
Oh,
nothing.
Okay.
It didn't make sense.
Okay. Okay, and just to announce that there is also this weighted setting in the infinite dimensional torus, but I'd like to say only a few words here. So we all know this AP condition for weights on Euclidean spaces. So we use some constant AP, which is the supremum, and we look over these constants, and the supremum is taken over elements of our basis. And on Rn, everything works perfectly. That we have the following characterization: that if our weight is contained in AP class, then it is if and only if maximal Hardy-Littlewood operator, say associated with cubes, is bounded on LP with on weighted LP with this weight. So we have the following characterization. And if we want to look at what is going on in torus, then what happens? So the first observation is that if we look at R0, then there is nothing interesting, because for all classes AP, the maximal operator is bounded for all Qs which are finite. So in some sense, there is no difference to which exactly class AP our weight belongs, because the result is the same. Okay, and if we look at the basis MR, then also nothing interesting happens, because this time, if we look at any AP class, then the maximal operator is not of weighted weak type, not of weighted strong type QQ, also for all finite Qs. So for these 2 bases, nothing interesting happens. And now our question is just what should be a satisfactory theory of weights? Should we look, for example, for intermediate bases, or should we look for another condition to express what it means to be a weight of some class? So just to raise another question. And I think it will be enough for today. So I would like to finish my presentation with a bit of Madrid flavor. So I would like to thank you for your attention.
Questions? I have a couple.
Oh, okay.
So first one is so your maximal operator cannot associated with the full base R cannot be bounded. Have you played modifying the maximal operator? So whenever one has a measure which is bad in the Euclidean setting, say, sometimes it's useful to define a maximal operator which instead of taking the average over a cube, it divides by a set, by a set 3 cube.
Yes. Okay.
I guess here, since the thing is about the things that are around the cube, doing the same thing would do the trick, right? And you would get a bounded operator.
Yes, I didn't do that, but okay. This theory should work if we deal with both. But here we have cubes, so one needs to just look at the details. But this is nice direction. I think I didn't do that, but okay. It seems to be reasonable to consider it like this.
I think it should work. But then the second question would be, maybe one can look for examples there and on the Euclidean setting with a bad measure of whether there are intermediate bases there where one finds these and this could point maybe at your open question. Maybe one can try to transfer the problem there and study it there and maybe get inspiration from there and then transfer to the torus, because the infinite torus seems to be like a space. You can think of it as a space with a nice metric but bad measure. Bad metric and nice measure, right? One could interpret, and if one makes that interpretation, maybe looking for inspiration in Rn, which is more familiar with a bad measure, could be of help.
Yes, this is a good direction. I would like to also mention that my talk was purely n-dimensional, but with n going to infinity.
Yes.
So this is like you said.
It's like dyadic again.
Okay.